From the music you listen to the colors all around you, our universe is just humming with this secret energy. And today, we're going to decode that hidden world of waves. So, let's dive right in.
Sounds like a trick question, doesn't it? I mean, one's a sound, the other's light. But trust me on this. If you stick with me, you're going to see that they are connected by one really simple but incredibly powerful idea. All right, so to really get a handle on waves, we've got to go back to the very, very beginning. We're talking about a concept that is just fundamental to how our entire universe ticks. So take a look at this apple on a spring. If you pull it down and just let go, what happens? It doesn't just stop, right? It bounces up and down, back and forth. That super simple act, that vibration, that's the seed. It's where all the waves come from. And this predictable, kind of rhythmic dance, well, it actually has a name. It's called simple harmonic motion. Think of it like the universe's own heartbeat. And what's cool is once you know what to look for, I promise you, you'll start seeing it absolutely everywhere. Okay, so a vibration just sitting in one place is pretty interesting. But what happens when that vibration starts to move, when it starts to travel? Well, that's when things get really interesting, because that's when we get sound. All right, check this out. We've got a tuning fork here, and it's vibrating, right? It's creating sound waves. Those waves are traveling down this tube and then bouncing right off the surface of the water. Now, here's where the magic happens. What do you think goes on when the length of that air column is just perfect? That is called resonance. See, every single object has a frequency that it just loves to vibrate at. We call it its natural frequency. And if you come along and give it a little push with a force that matches that exact same frequency, boom, the vibrations just build on each other. They get bigger and louder and way, way more powerful. And hey, this isn't just some stuffy lab experiment, you know? Think about pushing someone on a swing. Your perfectly timed pushes are what make them go higher and higher. That's resonance. It's also why a slightly unbalanced tire can make your entire car shake like crazy, but only at a specific speed on the highway. You've even used it if you've ever had to rock a car to get it unstuck from sand, building up that momentum with each push. It all comes down to one thing: perfect timing. Okay, let's add one more layer to this whole thing. Motion. You know that sound an ambulance or a fire truck makes as it races past you? That nee sound? The pitch gets super high as it comes at you and then drops way low as it moves away. Here's the thing, the siren isn't actually changing its tune, nope. It's the sound waves themselves getting all scrunched up or stretched out by the ambulance's movement. And that, my friends, is the Doppler effect. And we use this effect for some seriously cool stuff. It's the exact principle behind a police radar gun clocking your speed. It's how astronomers can look out into deep space and know for a fact that distant galaxies are moving away from us. I mean, even bats use it. It's how they can tell if an insect is flying towards them or away from them, all in complete darkness. How amazing is that? Okay, so we've got it. Sound is a traveling vibration, but it's definitely not the only game in town. Now let's switch gears and talk about an even faster, and dare I say way more colorful kind of wave: light. So yeah, just like sound, light is a wave. And all the different colors you see, well, those are just different frequencies of light waves. But here's the really mind-blowing part. Your eyes only have cells or cones that are tuned to pick up just 3 of those frequencies: red, green, and blue. That's it. And by just mixing those 3, our brains can create and see every single color you can possibly imagine. It's almost like simple addition, really. When red and green light waves hit your eye at the exact same time, your brain goes, ah, that's yellow. Green and blue light together, your brain sees that as cyan. And you guessed it, blue and red make magenta. And if you look right there in the middle, when all 3 primaries mix together, you get pure white light. And here's the takeaway. This is not just some abstract physics theory. No way. This is the tech that's literally in your pocket right now, or sitting in your living room. I mean, if you could zoom in super, super close on your phone screen, you just see millions of tiny little lights, red ones, green ones, and blue ones, all working together, mixing in just the right way to create every single image you look at. All right, so we've laid out the case that light is a wave, and that's how we get color. But how do we know? Like, how can we be 100% positive that light actually behaves like a wave? Well, there's one brilliant, almost ridiculously simple experiment that settled the debate once and for all. And this is it. This is the setup for what's known as Young's double slit experiment. And it's so simple. All you have is a light source, a barrier with two teeny tiny, very close little slits in it, and then another screen behind that one to catch the light and see what happens. So let me ask you this. If you think of light as just a stream of tiny little particles, kind of like tiny paintballs, what would you expect to see on that back screen? You'd expect to see two bright lines, right? One line for each slit. I mean, that's just common sense. But that is not what happens. Not even close. Instead, you get this really bizarre pattern of multiple bright and dark stripes. The light isn't just going through the slits in a straight line. Something else is going on. So, what in the world is happening here?
The answer is one word: interference. When that single light wave hits the barrier, it passes through both slits at the same time, creating two new waves that spread out and start to mess with each other. Now, in some spots, the peaks of those waves line up perfectly. They add together and you get a bright stripe. That's constructive interference. But in other spots, the peak of one wave meets the valley of another, and they completely cancel each other out, leaving a dark stripe. That's destructive interference. And here's the key: only a wave can do something like that. And again, this is not just some weird thing that only happens in a physics lab. Have you ever looked closely at the shimmering, swirling rainbow colors on a soap bubble or on a little bit of oil on a puddle? That is the exact same thing happening. Light waves are bouncing off both the top and the bottom surface of that super thin film, and as they come back, they interfere with each other, canceling out some colors and boosting others. It's beautiful, and it's all because of interference.
So, figuring out that light is a wave wasn't just, a neat scientific fact to file away. No, it completely unlocked our ability to control and manipulate the world around us in ways that have totally transformed, well, everything.
Once we understood the rules of how light waves bend, or refract, when they pass through something like glass, we could start crafting lenses. And once you have lenses, you can build telescopes to see galaxies millions of light years away, and microscopes to see the tiny little building blocks of life itself. We are literally bending waves just to see more of our universe.
I mean, we've gotten so ridiculously good at controlling light waves that we can actually trap them inside a single tiny thread of glass. There's this property called total internal reflection, where light just bounces perfectly off the inside walls of the glass, over and over again. It can travel for miles and barely lose any steam. And that right there, that's the tech behind our fiber optic internet, sending all our data across the globe as tiny little pulses of light.
So we've gone all the way from a simple little vibration to the global internet, and we've seen how sound and light are both just different kinds of waves. But here's one final twist for you. The double-slit experiment proved, without a doubt, that light is a wave. But other experiments have proven just as clearly that sometimes it behaves like a particle. The truth is, it's both. That simple rhythm of a guitar string and the beautiful colors in a rainbow, it turns out they're just two notes in a cosmic song that is far deeper and way more mysterious than any of us could ever imagine.